hydrodynamics in 2 dimensions, quantum Hall vortex fluids, please.
Hello, everybody. First of all, I would like to thank organizers for inviting me to talk here. And I'm going to concentrate on hydrodynamics in 2 dimensions today with examples of quantum Hall effect and vortex fluids. And the main idea will be to clarify the role of so-called anomalous terms, and namely which physically correspond to Hall viscosity. Is there any pointer? I probably use it incorrectly. Oh, okay. Yeah, good. So let me first introduce some hydrodynamic relations. So this is conservation of charge of some kind, and this is the conservation of momentum equations. And the right-hand side is external force due to electric and magnetic fields. And T is stress tensor, which is conventionally written this way in the simplest ideal to the hydrodynamics. So nothing here is about 2 dimensions. This is general hydrodynamic equations of ideal fluid. And if fluid is isotropic, we usually use gradient expansion and write additional corrections to the stress tensor of ideal fluid, which look like this. And these are viscous parts of the stress tensor. This is called shear viscosity, and this is called bulk viscosity. Here, VIK notation is for symmetric derivative of velocity and known as strain rate in hydrodynamics of medium. So if we have 2 dimensions and broken parity, then in addition to having these isotropic tensors delta IK and VIK, we can also use epsilon IK to construct our quantities, and in particular we can construct the following term, which is symmetric. So this is a symmetric part of the stress tensor, and it can be written probably in somewhat easier notations using this star. This star is just convolution of derivative with epsilon vector. And this term is known as Hall viscosity. It's also part of the viscous tensor, but it's not dissipative, and another name is odd viscosity, Lorentz shear modulus, etc. So what we're going to look for is we're going to look for this term in the hydrodynamic equations of fluids in 2 dimensions. So there will be 3 parts of the talk. First, I will give you example of fractional quantum Hall effect fluid, so this is based on the work published a couple of years ago. And then I will talk about anomalous hydrodynamics of vortex fluid in 2-dimensional incompressible fluid. And finally, I will tell you something what is in progress with the graduate student Gustavo Monteiro, who is very good. And this is some attempt of synthesis of different anomalous terms in hydrodynamics.
Sasha,
yes.
All these terms are pretty effective, right? I mean, what I want to say that, I don't know, probably I'm anticipating the question. Have in mind some theory like quantum Hall effect, which is really microscopic.
Right.
This term should be derivable from some.
Of course, right? Yes. And of course, I mean, I can phenomenologically write these terms because they're allowed by symmetries, but then the question is whether the coefficient in front of this term is 0 or not. And this, of course, can be only done using microscopic theory, which is underlying. So it will be mostly phenomenological. So what I'm going to do is I'm going to write phenomenological hydrodynamic Lagrangian or Hamiltonian to show that these effects are following from this formulation. And then I will try to fix coefficients, especially in the first part, which fit our known effects in quantum Hall effect. So this is the idea. Okay. So first part is fractional quantum Hall fluid. So this is the collective description of fractional quantum Hall fluid up to some corrections. This is the main result. So basically, result is that you can describe it using this simple Lagrangian, where you have 2 basically fields, pi field and rho field, 2 scalar fields, and they capture everything. Many things which describe which are collective features of quantum Hall states. And so these are conjugated fields, and Hamiltonian is expressed in terms of these quantities, which are itself expressed in terms of pi and rho again. So only two independent variational fields here, rho and pi, and everything else is just notations, but kind of suggestive notations, of course. So notice that this is not local. This phi is inverse Laplacian of density. So Laplace phi is rho. So you can say that it's formulated in terms of pi and phi, two scalar fields, or pi and rho, whatever you prefer. And beta is 3 for simplest Laughlin state, 1/3. Okay. So this, in principle, should remind you the famous formulation of quantum Hall effective behavior by Reed and then Zeng, Hansen, and Kivelson, which is called Chern-Simons-Ginzburg-Landau theory in terms of the complex scalar field phi. Indeed, if you make a substitution phi equals square root of density times e to the I pi, then you basically restore this except for this term. So this term is missed here, and I will argue that this is really important addition. Okay. So this picture is, everybody knows that. I just have to show it because it's about quantum Hall effect. And quantum Hall effect is two-dimensional electron gas in magnetic field, which forms new type of quantum fluid. I think this is citation of the Nobel Prize received by Tsui, Stormer, and Laughlin. And it can be thought about as some kind of quantum condensation of electrons coupled to vortices. It's incompressible, quasi-particles are gapped, have fractional charge and statistics, and the only low energy dynamics of the system is at the boundary of the system. And microscopics is captured by Laughlin's wave function pretty well. And I'm going to talk only about the simplest quantum Hall state, Laughlin state. So our goal is to find the effective classical hydrodynamic description of fractional quantum Hall effect. This is what's anticipated by Giuseppe. So we think about ideal two-dimensional fluid, so we don't need any dissipation, so we can, in principle, formulate it in Hamiltonian way. There should be some density-vorticity relation known in quantum Hall effect. If you increase density, vorticity at some point, or increase magnetic field, the density of the fluid increases at this point. So this should be incorporated into this hydrodynamics. It should be incompressible, should have Hall viscosity, which is known to exist in quantum Hall fluids, and should reproduce various linear responses. But of course, because it's hydrodynamics, it also captures some nonlinear physics, which and therefore has some predictive power. And of course, the interesting part is chirality and dynamics of the boundary, but I'm not going to talk about this today. Okay, this is very brief and incomplete history. The new piece which I'm interested in came in 1995 when Avron, Zeiler, and Zogrov noticed that there should be additional geometric transport coefficient, which is Hall viscosity in addition to Hall conductivity, and this started some subfield in quantum Hall studies. And this is what I'm going to use. Okay, let me go to Hamiltonian formulations of hydrodynamics in general. So this goes back to Landau of 1947, I think, probably even before that. So basically the idea is the following. Suppose that we have microscopic particles. We can introduce microscopic density rho, which is a function of space positions, and rho alpha here are positions of particles. And also the density of momentum, which is momentum times the delta functions at the place where particles are. So these are microscopic quantities. Nevertheless, by taking Poisson brackets of these quantities and knowing that P alpha and R alpha canonically have canonical Poisson brackets, or actually Landau in 1941 did it for commutators, so he did it for quantum hydrodynamics from the start. So we will easily obtain the following expressions. So Landau did not use charged fields, but if you use charge here A and introduce vector potential A, then you will have additional here magnetic field. This is some simple addition to those computation relations. Okay, here velocity is defined from the momentum density as such that momentum density is rho times velocity. Okay. So this is simple exercise, very instructive. And it's another simple exercise to show that if we have Hamiltonian, which is written like this, which is just rho v squared over 2 plus some functional of density, then by using those Poisson brackets, which were written on the previous slide, we easily commuting Hamiltonian, taking Poisson brackets of Hamiltonian with density, we obtain current conservation equation, and taking Poisson bracket of Hamiltonian with velocity, we obtain Euler equation in the presence of external fields. Okay. This is slightly non-standard stuff only because Hamiltonian formulation for hydrodynamics is not very often used in physics literature, but of course it is known well. So here, important thing is dynamics here is not necessarily vorticity free. We all know that for superfluid we can write Hamiltonian and variational principle easily, but this is much more general. So it can have vorticity which is distributed throughout the system. It's no problem. There is no such constraint here. Okay. So in particular, if we introduce vorticity as a curl of velocity, then using previous equations we can derive the vorticity conservation equation. So basically, well, in the presence of magnetic field, it's actually not vorticity, but vorticity plus magnetic field which is conserved. You can see that it satisfies exactly the same equations as density. Okay, and this leads to the following observation, that if you take some initial configurations of fields such that vorticity plus magnetic field is proportional to density, which is with some fixed coefficient, then this will be preserved during the evolution, because both vorticity and density are carried by the flow, and they do not change. So this constraint, therefore, which is vorticity proportional to density, and in constant magnetic field you can put it on the right hand side and call it ρ0. So this constraint, saying that vorticity is proportional to the deviation of density from some background, is respected by equations of motion. So if you put initial data satisfying this constraint, it will be preserved. Okay, this is just simple classical version. So Michael Stone in 1990 argued that this is the main feature of quantum Hall system. So this is what replaces in superfluid. It will be just the curl of V equals 0. And Hall effect is sort of like a superfluid. It's like a condensation, but of particles coupled to vortices, and therefore instead you have this type of constraint. So this is the feature of quantum Hall fluid. It's interesting to look at the dimensional. This is dimensional quantity. It's interesting to look at the dimensions of this quantity coincide with dimensions of h bar divided by m. So for such relation to exist, you need to have either specific initial conditions, or if you want this to be like a state, like it is in superfluid, then you really need to come up with some universal scale, dimensional quantity, and that can be h bar divided by m. Indeed, we will see that in quantum Hall effect, it's h bar divided by m multiplied by 2 pi divided by nu, where nu is Filling number.
The ρ also satisfy the equation of motion, no? They are
Say it again. So
ρ enter also the equation of motion.
Oh, of course, yeah.
This means intuitively, at a certain point you have a very high density of particles, you have a high density of vorticity, which intuitively you would say will spread out this density.
Right.
So will decreases. So
no, the way it goes is that you have.
Try to understand the consistency or self-consistency, mean field consistent of this equation.
The consistency is the following: that if you start with initial configuration where density is ρ0, nothing. So this is just background. This is the static solution. Then suppose that you have at some place bigger density, and proportional to the density you have vorticity. Start with this initial configuration. Then if this all moves, then vorticity always moves with excessive density. So it's the places where will be vorticity maximum, will be density maximum, and so on and so forth. So if you want to try to compress this fluid, it will rotate. The vorticity will increase. Okay. So hydrodynamics is generally dynamics of conserved quantities. So these are again expressions that I showed before. So if fluid is isotropic and we have this kind of term in stress tensor, it means that we have shear modulus. So it's not actually fluid. Because it's fluid, we say that there is no such shear modulus, so we don't write this coefficient in stress tensor. If you write this part in the stress tensor, it means that we have shear viscosity, means there is dissipation. So we don't want to write this one also. So the only thing we can come up with is basically this one if we assume that parity is broken and we are allowed to use this epsilon symbol. And this is known as Hall viscosity term. So V here is just symmetric derivative of velocity. It's strain rate. And so in this part of the stress tensor, this coefficient lambda is known as Hall viscosity or Lorentz shear modulus. And it breaks time reversal invariance and parity symmetry. For Laughlin states, we will argue that, well, we will not argue actually, people derived that this coefficient is expressed in terms of the filling factor for simplest Laughlin states given by these expressions. And Reed argued more generally that if the state is not the simplest one, then you have to use this formula where nu is a filling factor and h psi is a dimension of the vertex apparatus which I used to construct this whole state. So there is additional contribution. But for us it's phenomenology, so we're basically free to put any coefficient here if we want, until we derive it from microscopics. So the physical meaning of Hall viscosity is pretty transparent. It's the following, that let me first go over standard viscosity. So shear viscosity means that if I have a shear, the distribution of velocities of this type, then there is a friction between layers and there is a force which appears opposite to the gradient of velocity. This is shear viscosity, and there is of course dissipation here. And bulk viscosity is when I compress fluids and there is some kind of friction between radial layers, and it results in the force, in the radial force. It's also dissipative. But Hall viscosity is when you have a shear, you have a force which appears perpendicular to the direction of velocity, and therefore this force does not perform any work, and therefore there is no dissipation. So Hall viscosity, although it's part of viscous term, that the term viscosity is not, in many people's minds, viscosity means some kind of dissipation, and this is not. This is the part of viscous tensor which is non-dissipative. So in 1995, Avron, Zeiler, and Zograf basically computed the Hall viscosity for the simplest Hall states. And the way they did it is the following. They put the whole system on torus, which is characterized by the parameter tau, by modulus tau. And then they look for the geometric response of the wave function, Laughlin's wave function written on this torus with respect to slow changes of this modulus of the torus. And they basically derive the following formula, that this Hall viscosity is given by Berry phase type expression in terms of components of this tau, tau 1 and tau 2. Let me stress the analogy with quantum Hall conductivity, which is given by the following formula. So remember that quantum Hall conductivity can be derived as the following, that you put your state on torus again and put fluxes phi 1 and phi 2 through the basic cycles of torus, and then a diabatic transport with respect to those fluxes results in this expression for Hall conductivity. This is very similar expression, but instead of fluxes you use tau 1 and tau 2, which are components of the modulus of the torus. So you change geometry, change the metric of the torus. Yes?
I never understood it. This employing the torus in this calculation,
right,
is a trick, is essential, is fundamental, what it is. I mean, if I take, because something has to be local.
Right.
What can I care about the total Riemann surface?
This is actually a very good question. So you can introduce Hall viscosity and Hall conductivity as local responses of your fluid with respect to changes of external parameters. In the case of Hall conductivity, it's external magnetic and electric fields, and in case of Hall viscosity, it's metric. So basically, you can measure it locally by changing metric. That's a local quantity. So putting it on torus is a trick in this sense, but in a very deep trick, because when you put it on torus, you actually compute not just Hall conductivity, but Hall conductivity averaged over the torus. You compute Hall conductance, not conductivity. And similarly, like, I'm not sure that the word viscostance exists, but you compute somehow averaged Hall viscosity. And the argument in the Hall conductivity case was that the Hall conductivity itself is just local quantity, which depends on many things. But this averaged one is actually of topological nature, and it's quantized. And this is the one which is measured when you measure Hall conductivity in uniform experiments over large samples. So So torus both trick and also the way to connect it to topology and to quantization. So from my point of view, I'm talking only about local responses, so I will not need this global trick. So I will talk about local terms in the stress tensor. But if you really want to go and study the robustness of this with respect to impurities, and then you really have to study global properties and do things like that. That's a very good question. So the question is, okay, we saw already the simplest we know simplest Hamiltonian for fluid. So the question is what I should add to Hamiltonian to generate whole viscosity terms. And the answer is very simple. You just have to add term density multiplied by the curl by vorticity, by the curl velocity with some coefficient. And it turns out that the whole viscosity computed, if you write equations with this Hamiltonian, will be precisely proportional to this coefficient multiplied by the background density rho. Okay, so you can rewrite this expression in the following form. It's actually quite nice algebra. So if you open square here, you have v times gradient of log rho, which is gradient rho divided by rho. Rho cancels, and then you switch derivative, and you get this. So it's basically identity, except for this grad log rho squared term, which therefore I put prime here instead of here. And so this eta term can be absorbed in the velocity. You can try to forget about it. Let's call this velocity. But then Poisson brackets will change between velocity and density. So you cannot between velocity and velocity. So you cannot really do that easily. So you either you correct Hamiltonian or Poisson brackets. So but the effect is still there. The physical origin of this is actually pretty straightforward. And actually, it relates to the Reed's observation that the whole viscosity is proportional to internal angular momentum of particles, and which can be seen just this way. So let me write angular momentum of my fluid as r cross p, where p is rho v, the density of momentum, plus suppose that particles carry internal angular momentum mu. So I have to add mu times rho. Rho is the number of particles, and mu is momentum per particle. So then this can be written in the following simple way. Again, you can obtain this from this by taking grad star and acting on r, and then you obtain this one. So what you see is that this is actually modification of velocity by mu divided by 2 gradient star of log rho, which is precisely this. So this momentum per particle divided by 2 should be equal to eta. If you do that. So this is a physical explanation of what is going on here when you add this term. You basically take into account internal momentum of particles in the conservation of momentum, angular momentum. Okay. So basically, what I just argued is that adding this term, shifting velocity by this term, results in whole viscosity. But the question is how to take into account both whole viscosity and this whole constraint, which is that curl of velocity is proportional to density. Okay, and the answer is the following: that what you do is you say that velocity is not an independent quantity, but it's expressed in terms of the scalar field pi and phi, which is the inverse Laplacian of rho, in the following way. Then you see that automatically when you take curl of v, this term disappears as in a superfluid, but this will become Laplacian of phi, and Laplacian of phi is rho. So you immediately, automatically, you basically solved for v, which satisfies this constraint right away.
Then in the Hamiltonian or in the definition below, where is rho zero? Nowhere.
Rho?
Rho zero. The background.
Rho zero. Rho zero. This W is made out of external magnetic field. So if this, for example, this curl star of W is vector potential A, and therefore when you do curl V, you get curl A, which is B, which is if constant gives you rho zero. So it is there. It's just shift of this phi. And this gives equations of motion with whole viscosity, and whole constraint is automatically satisfied as I just argued. And you also can check that you reproduce Poisson brackets between velocity and densities if you assume that pi is canonically conjugated to rho. So basically, the answer is the following: that this classical Hamiltonian produces in Hall effect. This is free parameter for now because we talked only about phenomenology. But if you take this Hamiltonian and calculate the correlation of static density correlation, static structure factor, then to produce the result which is known in literature since Gerwin and Platzman, you have to put this coefficient to be beta minus 2 divided by 4. Beta is 3 for 1/3 state. Okay. So what I'm saying is that if you put this coefficient here, then you automatically produce correct result for static structure factor. So this is my way to fix this coefficient from phenomenology. This is calculated from microscopics, from Laughlin state, and now I just put it in my hydrodynamics to reproduce the right static structure factor. Okay?
You're treating this as a quantum Hamiltonian at that point?
No. So the whole story I'm talking about is purely classical.
So yeah, so the structure factor comes from...
Just density correlation function, static one. So you basically linearize it. You just do quadratic expansion in density, and you have delta rho times this stuff. So that's...
But the fluctuations which are present, where do they come from? The fluctuations which are described by the structure factor, where do they come from?
So I have to write the classical action such that if you put it in path integral, you will get right static structure factor. So this is purely classical stuff. But to compare it with fluctuations, of course, I have to add either thermal or quantum fluctuations, for example, to put this into path integral. But basically, to read the structure factor, I just have to take delta rho coefficient. But it's...
It sounds like, I mean, it's still it's not a quadratic problem, so it sounds like that would involve some approximation.
It's not quadratic problem. So this of course only knows about the quadratic part of this. Yeah. This comes just from linearization from quadratic part. My point here is that, and this related to fluctuations, is that if you put this coefficient here, as I argued before, you will get Hall viscosity, which is this, which is not correct Hall viscosity for quantum Hall state. The correct one is beta divided by 4. So this 2 is somehow necessary to reproduce static structure factor, but not good for Hall viscosity. So the question is, what should I do? What should I add to this theory to fix everything? And the point is that in quantum problems there are quantum zero motion, which is basically Landau diamagnetism, the fact that the energy of the lowest Landau level is magnetic field divided by 2. And I should take this into account into this Hamiltonian, because this is already classical effective Hamiltonian, which is derived and should include quantum fluctuations and the zero motion. So, and this is the answer of how to fix it. So it actually turns out to be pretty simple. So I take the previous answer with beta minus 2 divided by 4 coefficient here, which is good for static structure factor, and I add the energy of the lowest Landau level, 1/2 h bar times cyclotron frequency, which is basically magnetic field. And it seems to be totally innocent addition, because if magnetic field is constant, this is constant term, and this is just total number of particles added to Hamiltonian. So it should be totally forgotten. However, when I'm writing this term, what I mean is that you have to put here curl A, and when you write expression for current that is differentiated with respect to A, you have to take derivative with respect to A, variational derivative, and then it will result in the correction to the current, which is the curl of rho, the skew derivative of rho. Okay? So this term, although at constant magnetic field you can forget it, but it changes the definition of the current. Okay? And it turns out that if you do that and you just do calculations again, then you will see that static structure factor is not affected by this at all, because this is linear in density, so it doesn't affect quadratic part. But Hall viscosity, if you do this calculation for new current, which you identify with momentum, then you will see that it will be just sum of this term plus this term, and this 1/2 will be cancelled, and you will get the correct result. So basically, what I'm trying to say is that the full theory is and this is the main result, is this, then you have to write this Lagrangian with V alpha, which is just defined in terms of fundamental fields pi and rho in the following way. And coefficients alpha equals beta minus 2 divided by 4 to fix static structure factor, and eta is beta divided by 4 to fix Hall viscosity, to be correct terms. The true electromagnetic current is not rho times V alpha, but rho times V with different parameter in front of log rho. So this is the only parameter which changes Hall viscosity. And you have to, instead of alpha, you have to use beta over 4 for true current. Okay, and Hall constraint is slightly modified, but only up by higher derivative terms. It tells you that the curl of velocity is proportional to the density deviation from the background plus Laplace of logarithm density. So this results in some Liouville type equations.
Was there a term just in the density as well, a local energy? Or
say it again?
Was there a term just in the density as well, a local energy density proportional to rho? I think it was in previous version of the action you had at no, I mean right at the beginning when you were writing down quantum hydrodynamics at the beginning, you had a U of rho.
Yeah.
But there isn't one here.
There is no one here. You can add additional stuff here. So this is the minimal model. Of course, you can add here any function of density. This will give you some corrections. And in fact, you should. If you really want to study what's universal and what's not, you have to add various type of corrections. The reason I introduced rho there mostly because to show that I can absorb this log rho squared into U. But yes, here this is minimal part, and you have to write plus density functional. That's right. Okay, so again, for linear response, static structure factor is produced, Hall viscosity is reproduced. In fact, if you calculate calculate Hall conductivity from the same action, you will produce the Hall conductivity with higher order corrections in K. So the first one is the Z quantized Hall conductivity, but there is also higher term which is derivative, which is proportional to K squared. And this term was also obtained by Hoyes and so on using Galilean invariance before, so it also reproduces this. And you can do other electromagnetic and dynamic responses. In particular, just as an example, if you apply small electric fields and small magnetic fields, you can find, for example, which are time dependent and space dependent, you find that the correction to the density will be given by this equation. So you read here magnetoplasmon dispersion omega k given by this and so on and so forth. So there is a lot of phenomenology and you can use. Basically, you should understand that you can produce already a lot of phenomenology, because what I'm going to argue next is that this is almost the Chern-Simons-Ginzburg-Landau theory, which produces a lot of phenomenology of quantum Hall effect already. So this produces everything there plus few more terms because of this high gradient correction which we added to produce correct Hall viscosity. Okay. So again, this is what I promised. So we know that this expression, which is basically realizes flux attachment due to this Chern-Simons term to condensate of electrons, which are described by field phi. This can be written in hydrodynamic form. If you basically change variables here from phi to square root of rho times e to the I theta and do a couple of manipulations, then you will get this Lagrangian with coefficient 1/2 here, which comes from this square root. It's when you differentiate square root, you get 1/2 here. So, and this is wrong coefficient because it should be not minus 1/2 here, but beta minus 2 divided by 4. So you kind of forget this beta. If you just use this, you do not have this term correctly. And it turns out that it's actually very simple. If you just take this term and add it to the original Ginzburg-Chern-Simons-Landau series, then you will produce correct hydrodynamics with beta minus 2 over 4 here, which is correct one. And this term, of course, is again natural, as I argued, because this is essentially the density of particles multiplied by the magnetic field. So this is sort of zero fluctuations of particles in the magnetic field. Okay. So what I'm saying is that essentially everything I talked about is just amounts to adding this term to the Chern-Simons-Ginzburg-Landau theory, and then it will be as well as good. So this is intermediate conclusion. So Hamiltonian formulations of fractional quantum Hall effect is constructed. We took into account Hall constraint, Hall viscosity, linear response is correct, and there is a direct response to Chern-Simons Ginsburg-Landau formulations. And these parts I did not talk about, but you can make a direct connection to Laughlin's function and quantum hydrodynamics and actually derive from Laughlin function some of those parameters. I can show it at the end if I have time. And another important thing is that you can use as a starting point to think about chiral constraint and boundary dynamics of quantum Hall droplet. And there are a lot of analogies with Cologio-Sutherland model, but I'll skip that. Okay, any questions about that part?
Is it a natural incompressible formulation where you have constant rho divergence plus V?
So this is incompressible, right? Basically, it's incompressible effectively because of this constraint. If you have the curl of velocity which is proportional to density deviations, it means that when you try to deviate density, you have to create vortex, so you have to have the whole vortex field, and energy is huge. And therefore, it's effectively incompressible. I showed you in this response that actually there is this pole at omega k, and it's gapped, so it's constant. So therefore this is incompressible formulation. But it's not incompressible from the start. It's incompressible from as a result of Hall constraint. So it's a little bit different.
With the constraint, no?
Huh?
You did change a bit the constraint. You had the term which was the Laplacian.
That's right. Yeah, but this doesn't change. Even Hall constraint already gives you incompressible, effectively incompressible stuff. This log rho part is just gives you corrections to gradient terms, which fixes Hall viscosity, and higher k corrections to different quantities. Incompressibility you already have in the simplest case when you just say that Hall constraint is there.
I guess, and then again, more in the context of hydrodynamics, you can formulate incompressible hydrodynamics where you just deal with V,
Right.
and you can write plus or brackets for V or action for V.
That will be probably next part, related to the next part and the third part. So we'll come to that.
So this take into account all quantum Hall levels?
I specified it. So hydrodynamics, if I have one fluid hydrodynamics, this is basically phenomenologically what you can get. When I fixed coefficients, I talked about Laughlin state. So which means, and Laughlin state on the lowest Landau level. So if I go to the next one, the coefficients will change. For example, so it is known, for example, that for two-field Landau levels, the spin per particle will be 3/2. So the same as for 1/3 field Landau level. So Hall viscosity for two-field Landau levels is the same as for 1/3 of the Landau level. So my coefficient will reflect that. But basically what I'm saying is that if you give me some microscopic state, complicated one, then I have to fix coefficients in this theory to be compatible with that. And that requires independent calculation of these coefficients from microscopics. So I will probably show at the end if I have time or have questions about how to connect this to Laughlin state, but there are more powerful ways. Yeah.
So you start the derivation of this equation is purely classical. You look at it.
Right.
Then you try to make contact with some quantum system. So how do you know the domain of validity of this description? For example, to compute the fluctuation, you start from your classical action, you put it back to some path integral. So it's some kind again of
All right.
How do you know that you match with the original quantum?
The truth is that it probably depends on the quantities you calculate. Right. So what I expect this to work for is that if you apply external fields in some way and you ask what's the current flow and momentum flow, then this is good for, because this is what I optimized the system for. I basically optimized it in such a way that it produces correct momentum flows and charge flows. If you calculate something else, some correlation functions, or this is purely classical, and the only way quantum mechanics enters into this as its h-bar in parameters.
One justification could be some kind of mean field theory, or you forget about correlation.
That's probably right. So,
but then, so if this is correct, why you can use this action to compute the correlation themselves and fix the coefficient.
Right. So this is good for responses. So for the reaction of the fluid in the presence of external fields, this is good. For correlation functions, I mean, what's correlation functions in classical theory? In classical theory, I can only basically solve equations. So.
But at the same time, you use correlation to fix the coefficient.
That's right. Yes. Yes.
So like
well, yeah. So, for example, Hall conductivity. So what I can do is I can actually apply electric field, which is not constant in space, but has some k dependence. So it's plane wave, and then I ask what will be the flow of current, and to reproduce that, I need to add those coefficients in the theory. And this is purely classical statement of the problem.
So you can fix the coefficient just by linear response.
That's right. So all of these coefficients which I fixed can be fixed by linear response. That's true. And the question of whether it's applicable to nonlinear problems and how well it's applicable, it's of course the question. Yeah. Okay. Next example is vortex fluid. I'll just summarize basic results. So the problem is to describe a motion of dense system of point-like two-dimensional vortices which have the same vortex circulation, vortex intensity, both sign and magnitudes. So we assume that we have some kind of gas of point vortices and all of them are the same. And the question is, how does this configuration move? And some motivation comes from that this kind of systems can occur when you steer fluid, for example, in one direction, or actually in two-dimensional systems, it's known that cascade is going in opposite directions. So if you have some arbitrary two-dimensional system, the regions with large vorticity are formed. So the regions with vorticity of the same sign are formed naturally, and you can ask whether these regions can be described in the following way. Also, vortex strengths can be quantized, for example, as a result of superfluidity of quantum mechanics, or as a result of when you try to steer fluid at a fixed scale, so the size of the vortices is quantized or have some distribution around some value. And well, the system also is simple and reminds some integrable systems like Calogera, and also reminds Hall effect quite a lot, as you will see. So the main idea is we want to go from fast degrees of freedom, which is motion of fluid, because I have vortices, then close to the cores of vortices I have infinite velocity of the fluid. So we don't want to take into account this fixed but very fast motion. Instead, we will go to the coordinates of vortices as new degrees of freedom, and we'll look at the density of vortices moving. So, and that's the main idea, some kind of coarse graining. So naturally, the description which will be obtained will be valid at the distances much bigger than the intervortex separation. Well, the main result is that this system can be described by this equation of motion, which looks very much like Euler equation, but with additional term, which has additional contribution, which is anomalous. It also has this epsilon and looks exactly as Hall viscosity. This is Hall viscosity term. And the value of this anomalous coefficient eta can be actually computed for the system of vortices and equal to the circulation of the velocity around the vortex divided by 4. Remember that I assume that all vortices are identical, so they can be characterized by circulations of velocity around the vortex core. If you divide that circulation by 4, you will get this coefficient here. That's the result. So in this particular case, this coefficient is just the elementary vorticity of vortices. So starting point is the following. We'll start with incompressible fluid in 2 dimensions. So this dt means just convectional derivative is dt plus u gradient u. Pressure here is not independent quantity, but is defined from the incompressibility conditions that divergence of velocity is 0. And in particular, consequence of this is that vorticity is conserved. So it's known since 150 years ago that there is a solution, elementary solution, which is from Helmholtz and Kirchhoff, which is in complex notations, which are convenient when you, instead of velocity to components, you use complex velocity ux minus I uy. The following is the elementary solution of those equations. And this is just solution with one vortex at the point, with n vortices at points z alpha, which are time dependent, so these vortices move. And the vortices move according to this law. So basically, each vortex is dragged with velocity which is determined by the positions of other vortices at this moment. So these equations are first order. It's important to understand that. So this z alpha dot is just the velocity of the vortex alpha. So what we are going to do is we are going to basically take this solution with arbitrary but dense distribution of vortices, and we ask, how can I describe this solution at the scales much bigger than the inter-vortex distance? And for that we introduce density of vortices and the velocity of vortices through this formula. So we introduce it through the product density times velocity, which is given by this, and then we divide by density, you get velocity. Okay? So what I'm going to do is I'm going to derive equations for this rho and v, which are defined microscopically through the vortex positions. And of course, the main problem here is that it's all singular, and both vortex solutions and this expression, so you have to kind of resolve the singularity in the right way. It turns out that the way to do it is to introduce interesting relations between velocity of fluid itself, u, and velocity of vortex fluid, v, which is given by the following formula. I'll explain how where it comes from. So velocity, which we have to use for description of the motion, of the slow motion of vortexes, should be related to the velocity of fluid, corrected by the gradient of logarithm of density of vortices.
Just to be clear, V alpha is Z dot, Z alpha dot.
Z alpha is a position. Yeah. V alpha is the Z alpha dot at the yeah. There is no V alpha. Yeah, V alpha is here. Yeah, right. Okay. So let me describe the origin of this anomalous relation between velocities. First is technical, how you can do it technically. The simplest way to do it is the following way, in the following. So let's rewrite rho v in the following form. So v alpha, remember, are fixed at this point, the velocities of vortices, and this d bar is derivative with respect to z bar, and the known identity is that the d bar of 1 over z is pi times delta function of z. So if you apply this derivative here, you get expression on the previous page, which is v alpha times delta functions. So this is technical trick to rewrite rho v in this form. Then the next thing is we will substitute v alpha here, which is given by this expression. So we just substitute it instead of v alpha in this expression. We obtain the following combination. And then there is a trivial identity that this one is equal to this squared plus this. The way it works is that if you square this part and then bring it to this denominator, then there will be here there is alpha not equal to beta, and here all of them are. Therefore, you have to cancel this extra piece by this term. I mean, this identity is very easy to verify. This is really algebraic identity. So if you do this, you will see that rho v equals d bar applied here. D bar applied here. And when you apply d bar here, this will be d of rho, because d bar applied here will give you some of delta functions. And when you apply d bar here, you will get velocity multiplied by d bar multiplied by density. So, and as a result, dividing by rho, you will obtain the formula which is written here. So this doesn't explain anything. This is just technical trick of how you resolve singularities. You cancel singularity. Basically, the resolution of singularities is the following. On the left-hand side, they are naturally resolved because alpha is not equal to beta, so there is nothing singular here. This one is singular. So when you try to take velocity squared, for example, you always have singularities of the second order pole. But you cancel the second order pole by this additional term, which is the derivative term and which gives you this d log rho correction. That's technical remark. And physically, what actually is going on is the following, that if you really look now at the extra angular momentum, which is, so if you think of this of two fluids, one fluid is the incompressible fluid, and another fluid is the fluid of vortices, and you just compare what the difference of angular momentum densities between those two. So you have to multiply r times v minus u, the difference of velocities. And if you substitute v minus u as a gradient of rho, of log rho, and do algebra, you will see that it's actually proportional to the number of vortices in a patch. So basically what we are saying is that we are taking into account the fact that each vortex carries fixed angular momentum eta. And we want to include this by absorbing this angular momentum into the motion of the fluid itself, not thinking of this as internal number. So this is the same logic as it was previously done. And you can see immediately that this anomalous coefficient is equal to the half of the angular momentum. Half of the angular momentum per vortex is 2 eta, and anomalous coefficient is eta, which is half of that. Again, as in whole systems. Okay. So, and then we can write all equations. This is Euler equations with a stress tensor given by this, with redefined pressure and other quantities. And velocity and density are constrained here, as they should be for vortices. For vortices, essentially, if you know positions of vortices, you know velocities of vortices. So this is actually first order system. So the velocity there is not independent from density, but they are related by this constraint, which is very similar to quantum Hall constraint. Okay. So again, intermediate conclusion is that the collective hydrodynamics of vortex fluid was derived. Corrections to velocity field is compared to the field of normal fluid is proportional to the quantum of vorticity. There are anomalous contributions to stress. Hydrodynamics is Hamiltonian. I didn't talk about this much, but you can write Hamiltonian with anomalous correction, which is omega log omega, where omega is vorticity of the fluid or density of vortices. And in the presence of curved space, you will actually see that there is additional corrections from the curvature.
As far as I know, among vortices there are what is called Manus forces.
Right, yeah.
So you are able to derive all this effect to see attraction. What happens? They attract, they repulse. How shall I depict the motion of
you're talking about presence of curvature? Or?
No. In general, after you develop all this theory for the vortices, imagine I do a simulation. What should I...
I mean, it's what you can do. For example, if you can ask, this requires, okay, let me go next to this one. This requires careful treatment of boundary conditions, but the kind of problems you can solve are the following. For example, you have the bucket with incompressible fluid, which is rotating, and those vortices appear. You can ask, bucket has a boundary. You can ask what's the distribution of the density of vortices near the boundary. And this was actually solved some time ago with Khalatnikov, who had very similar corrections. And it turns out that in the narrow region close to the bucket wall, there is a suppression of density of vortices of a very particular profile. And that's just solution of those equations of vortex hydrodynamics in the presence of proper boundary conditions. So this type of problem. So, or you can solve, of course, standard hydro problems, like you have initial configurations, you solve for evolution. But more interesting probably is to look for some static solutions in interesting configurations, or in the presence of curvature.
I mean, this theory predict. I mean, I'm naive. I'm just trying to understand. Predict also annihilation of vortices of different vortices.
All vortices are the same size. No. Remember, this is Carroll's story. This is all vortices of the same style.
Then, if you want to consider two sets of vortices of opposite sides.
Right. Well, you have to introduce two types of densities and proceed. So people did similar things after Unzager, and it should be possible, but we didn't do that. There basically we have to think much more about how to resolve all the singularities. Here we use this technical trick, which is just good for vortices of the same.
What will be the difficulty?
Huh?
What will be the difficulties if you have become vortices?
in principle, should not be any difficulties. You'll have two densities of two species of particles. You have to introduce two velocities, two densities. You have some kind of two fluid hydro of interesting form probably. This is a very interesting problem because this one is probably even more relevant for turbulence and stuff like that. Yeah.
So in that case, will not be individually conserved the density.
That's right. I mean, if you include annihilation, so yeah, sure, yeah, that's right. Okay. Yeah.
One other thing, I think this is actually there's a numerical technique in fluid dynamics, I think, called vortex patch or something, where you actually model your flow by flow.
That's right. Yes.
And I think people even prove convergence to incompressible Euler flow, but I guess that's at vanishing vortex size. And what you're showing here is that
right. That's a very good point. You can ask the following question. Suppose that I have this vortex. So this is what people numerically do. So suppose that you have some distribution of vorticity of the fluid, and you want to mimic it so that numerically, for example. So what you do is you replace this distribution of vorticity by varying density of vortices of a fixed size. And then what you do is that you decrease the size of the vortex and take the limit of number of vortices to infinity, and you approximate better and better this continuous distribution of vorticity. And this is what people do numerically, and they have also analytical proofs that this is convergent procedure and so on and so forth, indeed. But notice what happens here is that as soon as I, for example, break each vortex in two, my anomalous coefficient is halved because it's proportional to elementary circulation. So what this anomalous coefficient is that memory that vortices are actually discrete. So in this sense, I'm doing sort of opposite. I have actually, to start with, I have discrete system of vortices, and I'm trying to model it as continuum fluid, but I'm saying that additional terms should be added to remember the size of the vortices. Yeah.
There might be a practical application to actually correct these simulations, presumably.
Right. So if you really want to take numerical simulations which are not going all the way to infinitesimal size of vortices, but as a finite one, then you can try to compare the numerical solutions with solutions corrected by these gradient terms, and that should be much better agreement. Yeah, that's a good point. Yeah, I didn't think about applying it this way. Yeah. Okay, so I do not have time, but I have only 3 slides left. So let me just try to describe you more general feature. So the idea now is to, and this is in progress, so this is not done. So there will be no slide with main results. So basically, suppose that we want to study generally anomalous terms in 2-dimensional hydra, and what would be the efficient way of doing this? And we are doing this with gradient student Gustavo Monteiro. And it turns out that there is a very powerful way of writing variational principles for hydrodynamics based on just symmetries. So this is a particular case for Galilean invariant first-order hydrodynamics, but it can be generalized in many ways. So the idea is the following: we write this action, and this should be understood as the action with 6 variational parameters. So first of all, this V here is not independent field but just notation. It's actually made out of 3 parameters, theta, alpha, and beta. And this is called Clebsch parameterization of velocity. So 3 parameters here. Then you have density, rho, which is just variational field, and 2 components of J, which is sort of current. Okay? So the claim is the following, that if you take this and write 6 equations of motion but varying with respect to all of them, then by manipulations you can come up with these 2 equations. One is that can be recognized as a charge conservation, and expression for J will be rho times V.
So this is an input?
No. This, if you take variation with respect to J, you immediately get V equal minus J divided by rho equals 0, which means J equals rho V. So J and rho are not dynamical fields. There are no time derivatives of J and rho. So these are like constraints. So when you vary with respect to J and rho, you will get actually not dynamic equations, but constituent relations between different quantities. So in particular, this one you obtain when you vary this with respect to J. Okay. So this is the one equation that you obtain. Another one is this one with T which is given by standard expression, can be found in Landau-Lifshitz. Okay, and this is pressure of the fluid. Okay, any questions about that? This is actually quite tricky, because if you really try to write variational principle for the hydrodynamics in terms of rho and v, you will be in trouble, because of the degeneracy of symplectic form. It cannot be inverted, so it will be complicated. It's known how to resolve it for already more than 100 years. The resolution is the following: that instead of velocity, one should use three fields, theta, alpha, and beta, as variational parameters, and then do reduction, so to express all these equations in such a way that these parameters separately do not enter, but only velocity enters. And this is the way how it's done. Okay, so this is very standard hydrodynamics. So this is just variational principle for hydrodynamics, which is in the first page of Landau-Lifshitz. So this is just variational formulation. What we can do is we can ask what type of gradient corrections we can add to this hydrodynamics, and what are the consequences of these gradient corrections. And this will be studying these anomalous terms. So the origin of these anomalous terms, which I use so far, is the following: that if you take a charge conservation, which is this one, you can come up with two identities. The first one is just trivial. You don't even have to have charge conservation. It's just that the curl of gradient is 0. This is basically what it is. It's identity, obviously. But if you use also this charge conservation, then you can take time derivative of the skew derivative of density, and after few manipulations you come up with this expression, which is written as the divergence of the stress tensor with the whole viscosity contribution made out of J, if you compare with the previous notations. So basically what I'm trying to say is that if you, for example, redefine your momentum by skew derivative of rho, so instead of this you have P plus this, then your stress tensor will change by the same coefficient multiplied by this. So you will change whole viscosity by gamma by just adding this identity multiplied by gamma to your momentum conservation equation. So this is ambiguity. So it's basically, it means that until you tell what exact expression of your momentum is in terms of rho and v, you really don't know what whole viscosity is. So you can change it by adding this identity to it. Similarly, you can change what the definition of current by adding this identity to the current conservation equation. So you can redefine current by this, and then you will change quite a lot of things. And physically, it means that here I assume that every particle has magnetic moment alpha, and here I assume that every particle has angular moment, I forgot, 2 gamma or gamma over 2. It's proportional to gamma. Okay, so basically, when I give you equations of variational principle in a flat background, so there is no metric, no external electromagnetic field, you really do not know how precisely to define current or momentum density. And you have, because of the charge conservation in this case, and just because of this identity in this case, you really have freedom of changing those. So the way to fix it is to write your action in the presence of non-trivial geometric background. In particular, we already saw that if you add term to the action, to basically this action, if you add term of the type this alpha coefficient multiplied by magnetic field times rho, that tells that when you vary with respect to A, you will get d star rho, and that will be correction to current. So this term added to the action changes the definition of the electric current. But to see this term, you need magnetic field. If magnetic field is 0, you just don't see this term. It's just integral of number of particles, which is conserved quantity on its own. Similarly, if you really want to see the true definition of momentum density, you have to add this term, where U is a new part of Newton-Cartan background. And I'm done. So basically, the outcome of here is that you really can do it in several ways. You can resolve these ambiguities using microscopics and some kind of microscopic calculations for particular system, or you can try to start with the system written in the presence of curved background, and then you have this. You can just read this from the action. And there are many reductions of that hydrodynamic formulations and generalizations. Generalization is that, of course, the most interesting one is that you can use the following Clebsch parameterization of velocity with 2 additional fields, and this is suitable for finite temperature hydrodynamics. It's quite surprising, but finite temperature hydrodynamics also Hamiltonian and can be in the absence of viscosity and can be also described in this way. So this is generalization, and there are also reductions. You can make fluid incompressible by putting ρ equals constant in that action. You can make it superfluid by dropping alpha and beta in parameterization of velocity. You can consider whole fluid by saying that velocity is related to density and theta and dropping alpha and beta. You can consider fluid without charge conservation. This is the most interesting part, which I'm working on right now, because we saw that this all ambiguities come from the charge conservation. So it will be interesting to look at the fluid where charge is not conserved. For example, something like phonon fluid. So then you just drop theta, because this is the variation with respect to theta, which gives you current conservation and parameterization of velocity. Or you can look at the Galilean invariance. In the Galilean invariant system with one species, momentum is proportional to current. And this is what we used in Hall effect. Therefore, this alpha and gamma should be related in the Galilean invariant system. And yeah, and this is basically it. All of this is sort of understood in the linear response in the linear response context. So thank you for your attention. And tomorrow I'm going to talk at Cavendish lab, and talk will be geometric response of quantum Hall systems, where we'll talk about linear responses and those non-trivial backgrounds of quantum Hall systems. That's it.
Thank you. We had many questions on the seminar. There are something left. Another question left. Or people are very young, I have to say. Okay, if not, let's take Sasha again.